Today I'm going to be talking. Today I'm going to be talking about a project that we carried out through Safety 21 this past academic year. And the project ultimately created what we call SALUSLux, right? Salus referring to safety, Lux referring to light, which is essentially an open source simulation toolkit that we built to help researchers and cities evaluate how well their intersection lighting designs are working, and also to assist with planning. And in particular, the goal was to have it really focused on pedestrian safety as opposed to just vehicles. And it was really interesting. What we found were that a lot of the challenges that have been sort of, or I would say that we're able to, through this work, challenge a lot of sort of wide assumptions in this space to help make intersections safer, but super excited to talk about it with you. I was about to go into depth, but let me do introductions first real quick. So first, I'd like to tell you a little bit more about me as well as our lab. At CMU, I run the Sustainable and Livable Urban Systems Lab, or the SALUS Lab. And specifically, we're really interested in understanding how things like new data and intelligence can be embedded within design and decision-making processes to uncover and sort of leverage these human-centered benefits and goals of our infrastructure system around us. So to give you a little bit of background about this project, Steve Quick from Architecture, a fantastic collaborator, reached out to me a couple of years ago wanting to kind of talk about this idea that had been tossed around in architecture about, hey, the city of Pittsburgh is, undertaking a lot of innovations and redesigns of their lighting infrastructure, moving towards LEDs. And at the same time, we have a really strong cohort of folks who study things like DarkSky principles here at CMU. As they start to kind of, integrate these new technologies into the city, who's kind of thinking about how we balance all of these trade-offs and benefits. So we put in this proposal, and Steve was really the, I'd like to say, brainchild of this project. And the person who carried out the project was Korowich Kave, who is really fantastic. His doctoral research really focuses on walkability and how we perceive the built environment. So when Steve brought up this project, I immediately thought of Korowich, and he did a really great job, so thank you. So jumping right in, let me start with sort of why this work matters. So in 2024, more than 7,500 pedestrians were killed on American roads. And this is not a static number, right? So it represents a 75% increase since 2010, meaning, of course, we are moving in the wrong direction. And what makes this even more troubling, of course, is that this crisis does not affect everyone equally, right? We're seeing older adults, people with disabilities, for example, disproportionately impacted and represented in these fatalities. So, of course, our big question here broadly is, what can we do about it? Well, when you look at the data, right, a striking pattern starts to emerge. We see that these pedestrian fatalities are predominantly happening at night. And they're not actually happening, it's not represented here, but they're not happening sort of uniformly throughout the night. We're typically seeing that these fatality rates are spiking approximately 20 to 50 minutes after sunset, and they remain elevated for several hours into the evening. So this coincides with when pedestrians, bicyclists are still really active during that time of day and really putting people most at risk. So again, our idea was that if we're going to be serious about reducing these pedestrian fatalities, then we're going to also have to be really serious about considering what's happening after dark. And of course, there's a silver lining to this, right? Because we know lighting works. Should be obvious. It's one of the most effective interventions that we have. We don't have to build new infrastructure necessarily. We can retrofit. And we've seen public lighting associated with a 65% reduction in nighttime fatal accidents, with additional reductions in nighttime crashes with vehicles ranging from 13 to 75% following new or improved lighting installations. But I'd like to say and also emphasize this is a very, very critical but here. More light is not necessarily better light, right? So that's really important to this thesis. So excessive lighting or poorly aimed lighting, for example, can create things like glare, reduced visibility, cause discomfort, right? So the question is not just, how much light do we need, but it's what kind of light, where is it going to go, in what directions, and what is it going to be evaluated by, what standards exist. So these is sort of where we started to see things get complicated. So to give everyone kind of a little bit of a background here, the roadway lighting system that we have today was not designed for pedestrians, right? It was designed for vehicles. So all of the standards we have in lighting, all of the metrics, the placement conventions, things like this, all of it was built around this question of, can a driver see the road? Not, can a driver see a pedestrian trying to cross it? And the technology shift at the same time has been challenging this, right? So while we've seen amazing strides in longevity and energy efficiency with things like LEDs, this introduction has brought about a lot of really new challenges. So for some context, LEDs are directional, meaning that a pedestrian standing just a few feet away from the beam cone can be easily invisible, even though we can see the pavement around them very clearly. LEDs can also produce significant glare, right, which you're seeing right here, that impairs visibility, especially of drivers. So we've seen that even these LEDs that are marked as like warm white still emit proportionally more blue light than the old high pressure sodium fixtures that they have replaced. So what we're basically seeing in this transition is that we've swapped in a new technology that's more efficient, but it's also more directional, more glare prone, and basically causing a lot of new safety issues with pedestrians that we have no way to regulate. So let me talk a little bit here about some of the metrics for a moment, because I think this is really at the heart of the problem that you'll have to understand. So there's three sort of standard ways to measure illuminance, right? Illuminance is that amount of light falling on a surface. So we have horizontal illuminance, which measures, you can think, light hitting a ground plane. And this is the metric that's most commonly used in all of the standards. We also have vertical illuminance. You can imagine this being exactly directly what the driver head-on is looking at. And then we also have semi-cylindrical illuminance, which sort of wraps light around a vertical cylinder. So this is sort of the closest proxy that we have to, say, a human being. And something that's really important about this is you can imagine when people are, say, turning directions around a corner, that's where this semi-cylindrical illuminance really comes into play. Okay, so we have these three metrics, but here's the main problem, right? So a score, something that scores beautifully, like very strongly in terms of safety, in terms of visibility on a horizontal illuminance plane, right? Lots of light on the pavement doesn't mean that it necessarily performs well with regard to the vertical or the semi-cylindrical illuminance. So you might be able to see the pavement, but a human can be nearly invisible to see at the same time. And yet, and I said this before, right, despite this, we're still seeing horizontal illuminance remain sort of that default metric that's most practice and compliance checks are based off of. So in many respects, we hypothesize that we're sort of optimizing these standards around the wrong thing. Now, there's one more tension that I also want to point to in this space that cities very practically are facing. So on one side, we have organizations like DarkSky International, who are recommending color temperatures of around, say, 2,200 Kelvin. You can think of that as being sort of like a warm amber light. And they're recommending this for all outdoor LEDs. And of course, this is to reduce things like light pollution, for sustainability efforts like minimizing ecological disruption, and also promoting consistent circadian rhythms. But on the other side, we have this visibility research, right, which is showing that temperatures closer to 3,000 or 4,000 Kelvin are what we need for safety. So cities are basically hearing two sides of the story, right? They're saying if you want to be safe, you're going to need brighter and cooler. If you want to be sustainable, you're going to need warmer and dimmer. And they're kind of stuck in between these two things. But what if that trade-off, and this is kind of, what drove this work, what if that trade-off isn't as real as we think or that we're, assuming, right? So what if the right sort of spatial design of these streetlights could make warm, dark sky friendly lighting safe for pedestrians, right? So we don't want to have to give up either one of them. So that was sort of one of the main questions that motivated this project. So diving in a little bit deeper, the research was really organized around two central questions, right? Very practical. So first, how does the combination of light source characteristics, so you can think things like beam distribution, wattage, color, temperature, interact with the spatial geometry of these street lights around them, right? So things like their height and their offset, their orientation, even their manufacturer, to really influence pedestrian visibility at intersections. So this question was really deliberately framed as sort of that interaction piece. And the second question we have was, can lighting designs that perform well for pedestrian safety also meet acceptable thresholds for minimizing light pollution and visual discomfort? So in other words, can we have the best of both worlds? And the underlying these questions, of course, were several key contributions of this work that were very tangible and useful for potential city planners. So first, we developed an open source, reproducible street lighting software framework, SALUSLux, that integrates photometric inputs, intersection geometry, those external parameters, as well as internal parameters having to do with the light. We produced a multi-objective evaluation approach that treats the pedestrian safety, visual comfort, and sustainability outcomes, for example, as sort of coupled design criteria. And we aligned those established guidelines and glare assessment methods into it. And third, we carried out a large parametric intersection case study that really aimed to demonstrate how commonly adjusted design parameters would reshape these lighting properties, right? So you can think of this as sort of motivating this idea of having the design space exploration rather than just having one-off evaluation. So one thing that's important to note is, why did we need to build some new toolkit from the ground up, right? Why not just use existing software? So to give you some background, the two most widely used tools in lighting design are Dilux and Relux, and they're really fantastic at what they do, right? They produce renderings, they do compliance checks, and they can look at a handful of other different types of designs. But they have a couple limitations that really prevented us from being able to just use them and, run with them. So first thing is compatibility, right? So we're going to see that IES maintains a standard plain text file format for their photometric data that virtually every manufacturer worldwide uses. And unfortunately, they have very proprietary, they have paywalls, they have proprietary formats that they use for these files, and it really prevents us from being able to explore new types of, say, lighting patterns. Second, these tools are also built around very manual graphical workflows. So everything is based on, point and click, which means that, sure, we can put in a lot of time to do one test at one geometry for an intersection. We can get great results, but then we can't do that 2,000 times to see what could be better, right? So when we think of like the city of Pittsburgh wanting to scale their decision making, what exists, it's just not going to be able to provide that. So we built SALUSLux from the ground up, and it's, again, I mentioned this before, but an open source Python-based simulation toolkit. And again, not just meant for research purposes, which we're going to be focusing on today, but really for practical use by stakeholders. So I'm not going to go into the weeds of this. I'm sure Korowich would love to share that with you if you ever want to chat about it. But I do want to give you kind of an overview of some of the key functions. So it first reads in these standard IES files that I told you about and parses them, right? So we can take them from manufacturers. We can also create new ones, for example. These files contain then things like luminous intensity distributions of a fixture, right? So essentially you can think of how much light it emits in every direction. We read the files, handle the various symmetry conventions that manufacturers use, and then basically are able to reconstruct and back out a three-dimensional light distribution from this that we can model. We also do things like interpolation to make sure that we can estimate the intensity at angles not prescribed by the manufacturer. So the second module in SALUSLux then generates an evaluation grid, right? So this is going to be the mesh of all of the points across the intersection where we're going to be calculating these lighting metrics. So every point on this heat map, for example, is one of those points in our grid. The third module computes a luminance. So for every point on this grid that you can see right here is basically calculating things like the horizontal, vertical, semi-cylindrical illuminance. This is a completely adjustable parameter, but we're calculating it at about 1.5 meters off the ground as sort of a compromise between, facial and body recognition of the pedestrians, as well as the height of people sitting in their cars. From there, we compute luminance, right? So this is kind of, you can think of how bright the surfaces appear to be. And we do this using a reflectance model that we integrate in using just, for this case study, default asphalt references that you can find from the literature. And finally, it also computes the glare rating using CIE standard formulas, evaluating sort of a worst case glare from both the drivers and the pedestrians' different perspectives across 8 different sort of cardinal viewing areas that these might occur. And all of this, of course, is just running automatically for every scenario that we want to consider. So it's pretty simple the modeling isn't simple, but what we get is simple. We end up getting a CSV file with the things like the minimum, average, maximum values for every metric on the surface, the geometric surface that we're considering. And of course, we also get the full set of spatial heat maps to be able to analyze. And one thing I want to emphasize here is that for our case study, which I'm going to show next, we're doing just a classical 4-lane intersection, but all the geometric properties of these roads, whether it's an intersection or a crosswalk, can all be input manually to whatever your configuration is. So for our case study, again, we used just a standard 4-way intersection here. You're going to note that these are kind of the different key areas that cars and pedestrians can be in. For the sake of complexity, we typically start looking at averages over these areas. And we define the parametric design space. So we had 2 main categories of variables that we considered. So we had external and internal parameters. Things like pole configuration, mounting height, offset to height ratio, so how far away is it from the intersection, in addition to the internal parameters, right? So distribution type, wattage, color temperature, and manufacturer. And once you combine all of these together, we had about 2,304 unique simulation scenarios per test that we would run. So to compare all of these 2,000 plus scenarios and to put them on sort of a level playing field, we developed a scoring framework that was rooted in the literature. So you can see here that we established sort of performance thresholds, you can think, drawn from things like FHWA, guidance, ANSI, IAS files, and standards. And basically for every single surface that we have, so you can think of these areas here, we would be checking basically, hey, does this metric meet this threshold for this given area? And basically be assigning points that can be weighted based on your stakeholder preferences or aims. So for this talk, just in terms of being interpretable, we normalize everything to a 4.0 scale. Just think of like a GPA, for example. Everyone can relate to that. So 4.0 here is going to mean that everything was satisfied across all of these areas. And like I said, and I do want to emphasize this, that we consider everything kind of equal. We have equal priority right now to sustainability that we do to safety, but these parameters can be changed based on your stakeholder needs. So here's sort of the big picture before we go down a little deeper. So this is what these 2,000 plus scenarios look like, right? So we see this histogram. We do have sort of a bimodal shape here, a little bit left skewed, but we're seeing that the majority of these cases are sitting below 3.0, 2.0, for example. But what's really important to see here is that even when we do consider things like sustainability and safety, we have a considerable number of cases that are sitting at that 4.0. So the next question is really what distinguishes these really high-performing situations that can balance trade-offs really well, and what sort of distinguishes them as those top designs? So we explored two configurations in this study in particular, and I'll explain what those are. They're both variants of what we would call sort of the turbine layout. So to kind of think about this, the 90-degree configuration sort of places the four poles in sort of a box shape. This is what you would typically see at your intersection. And when I refer to the 45-degree format, we're referring to all the lights pointing inwards into the middle of the intersection, kind of like in the shape of an X you can think of. So these heat maps here are basically showing how each configuration's best score varies with things like pole height and offset to height ratio. So two things that I really want to point out here are that we see that the 90-degree angle, so this is A right here, is very brittle, right? So when I say brittle, I'm referring to the fact that as you increase things like the pole height, performance drops, right? And as you increase offset, the performance drops. And it's very highly sensitive to both of those parameters. And this makes sense physically and is, aligned with the research in this area, where we have higher poles tend to reduce that near field illuminance and can also increase things like glare, which is where we start to see that trade-off. The larger offsets that we're seeing it's sensitive to also push a light away from the pedestrian zones that are going to matter most to us. And then when we look at the 45-degree layout over here in plot B, in contrast, we're seeing something very different, right? We're seeing that the performance tends to stay pretty consistent across variations in both height and also offset. And intuitively, this makes sense to us, right? Because in this orientation, the distributions of the light across multiple pedestrian-facing directions include both the approach and also the ways that cars would be turning around the corners. So again, the takeaway here is basically that the geometry is going to have a really, really big impact on the performance, and that in general, the 45-degree configuration performs better in certain cases and is also more robust as a starting point. So let's also look at the internal parameters here, right? So I have IAS type here on the y-axis, and then we also have wattage. So when we have this 90-degree layout, the best performance tends to come from this type number 5, right? But it also comes at a very high wattage. So essentially, to make this layout work, you're going to need to flood the intersection with light from all different directions, right? It's expensive, it's energy intensive, and it contributes to things like light pollution. For the 45-degree layout, though, right, we see this in plot B here, multiple distribution types are having top scores here, right? So we're seeing it in type 2, type 3, type 4. And importantly, we're even seeing this happen now at lower wattages, right? So we're getting better trade-offs there. It's basically telling us now that this luminaire's beam distribution pattern is going to be a major factor in the performance of these different models. So putting those just kind of the external variation on top, internal variation on the bottom, this brings us to a really critical point and sort of interpreting these results, right? It's telling us that we cannot optimize geometry and the luminaire properties independently, right? They're highly interrelated. So this has a really practical sort of implication for cities, right? So if a city wants to say, and this is what's typically done, we're going to standardize on type 2 luminaries, right? That might be great if they're also using a 45-degree configuration. But if they're using 90-degree, we're going to see those drawbacks, right? So this kind of blanketed approach of treating all intersections the same, this is where we start to see those vulnerabilities. So let's dive deeper into one of those 4.0 scenarios real quick. So let me show you a bit more about what a perfect score looks like. So this is scenario 414 we'll refer to. And as you can see here, it uses a 45-degree configuration with a 6-meter pole height, 2700 Kelvin, and an offset ratio of 1. And it's type 2. So these 6 heat maps here, which is like the standard output from SALUSLux, shows the spatial performance across the entire intersection here, right? So The top left is showing horizontal illuminance, the middle is showing vertical illuminance, and on the right we see semi-cylindrical, which is having really strong performance. And this makes sense, right? Because a pedestrian in these zones, like I said before, is going to be visible both from oncoming traffic and also people who are turning those corners, which is where we see a lot of these issues arise. And below those, we have glare, right? So including on part A right here, the worst case glare from any direction on the left, and we have driver specific in the middle, and then we have from the pedestrian's perspective on the right. So basically it's just giving you an idea of what is an output from this. And every applicable metric we'd say on every applicable surface can be assessed and is meeting that minimum threshold in this particular case. So looking at this particular scenario, right, this was number 414. Among the others that also had a 4.0, we saw, again, just as a recap, that 414 uses the 2700 Kelvin color temperature. And going back to kind of where I started, that is this warm amber light that does align with dark sky principles. So that's really, really fantastic, right? So if we go back to that conventional wisdom that I opened with, this idea that if you want to maximize safety and visibility, you need that cooler, wider light, things like 4,000 and above. And if you want sustainability, you need those lower ones. We're able to strike a really nice balance between both of those. And we think this is significant for policy, right? Because it means that cities don't necessarily have to be compromising one or the other. Of course, there's also a couple of trade-offs that we're always going to have to consider along the way. But again, these are very difficult to understand with just standard Dilux, Relux type platforms. Really easy to use with SALUSLux. So I'm going to give you just kind of two very small case studies, one in trespass and one having to do with kind of delayed interval timing, just to show you some of these capabilities. So light trespass is basically this idea that when we're trying to light an intersection, there's going to be this spill into, say, residential areas next to the intersection. So we investigated this, right? Now you can see that we have these spillover areas in the corners by taking our best performing scenario and then sort of varying the pole orientation from 90 degrees to 45 degrees to kind of see if the conventional is worse or what happens. And as we expected, I would say, the horizontal illuminance on these adjacent areas of land right here increased as the angle went from 90 degrees to 45 degrees, right? We also did this for vertical and semi-cylindrical, and we saw that the illuminance of both the vertical and semi-cylindrical was higher than the horizontal at each one of these locations. But I think it's important to kind of look at what those differences actually look like, right? So we have 90 degrees down to 45 degrees. And we see that even with the very standard 90-degree configuration that we typically have, we still have issues with light trespass, right? The problem already exists. And these current trespass regulations are very sort of like, we would say, blunt instruments right now. They sort of apply these fixed caps uniformly in all directions, regardless of whether that light is going to be shining into some empty lot or someone's house, right? And what this analysis is basically suggesting, just as a tiny case study, is that we need orientation-aware trespass standards, right? So standards that can also weight these limits based on the context of what is around them. And we need to be considering things like vertical and semi-cylindrical illuminance within these areas as well, because this is essentially how it's going to be perceived. Now, I also want to briefly touch on one more finding from sort of, I'd call it the extended analysis, where we are looking at some different capabilities here. Because it connects to design and signal operations, which again are always considered with the city. So you're probably familiar with this idea of leading pedestrian intervals. So if the light has ever turned green for you and you've seen that the pedestrian can start walking before the cars get to go, that's what I'm referring to, right? So it's usually around 3 to 7 seconds long before the vehicles can get that green light. But of course, there's an important nighttime visibility part to this that people aren't really considering, right? Because at night, it's basically giving pedestrians a head start to get into that better visibility that they wouldn't otherwise have. So we used SALUSLux to basically map the semi-cylindrical illuminance along the crossing path. So you can see here that we're considering both situations where you're walking sort of first into the incoming traffic and then outgoing, as well as the other direction going back. And for pedestrians who were entering from that incoming side right here, the peak illuminance was happening about 2 to 3 seconds in, and when you were coming from the other side, it was about 7 seconds in, right? So depending on the configuration of your intersection, the city could now be looking at automated ways to be able to time these leading starts for pedestrians in a way that's most efficient, right? Why give them 7 seconds when 2 seconds is safe enough for them to go across, especially when we need to maximize throughput. Alrighty, so stepping back from the very specific findings here, I do want to kind of start closing out and talk about what this study sort of tells us about how we should be evaluating intersection lighting going forward. So across all the scenarios we tested, I know I've emphasized this a lot, but that semi-cylindrical luminance was the most difficult metric to satisfy, right? So it had the lowest average score, you could say. And this did make sense, right? Because it's the most also demanding metric, right? It captures that visibility from multiple directions, not just head on or from the ground. At the intersections where turning vehicles approached pedestrians from, say, oblique angles, right, coming around that corner, the three-dimensional visibility is the thing that is going to matter most, right? And it's what governs. Third, we saw that our results strongly suggest that semi-cylindrical illuminance should be elevated really to a required metric for crosswalk lighting at intersections. And again, that's because it's the metric most closely tied to how pedestrians are perceived, particularly by drivers. And conversely, the horizontal illuminance, which is that metric that's most commonly used in practice, offered really limited additional information or value to us once the other metrics were satisfied. So this is basically saying that over-reliance on horizontal illuminance like we're doing can actually be somewhat counterproductive to us, right? Because it's not the thing we actually want to optimize. And it can ultimately lead to excessive lighting that can then raise glare and light pollution, quite frankly, unnecessarily. And then sort of the bottom line here as like a recommendation is that we need to start shifting from roadway-centric compliance checks towards more human-centered performance metrics, right? So evaluating intersections based on how well the driver can see a person, not how bright the pavement looks to the driver. Now, the research findings I've shared are important, right? But I want to emphasize that this is not just a research tool. This is meant for cities. I thought this was an awesome image from Etsy, actually. Someone's selling posters of all the bizarre intersections that you see in Pittsburgh. So it was too small, but you have actual intersection names, downtown, Squirrel Hill, suburbs, all this stuff. And I mean, this is the kind of tool where you can actually start looking at these really bizarre intersections and trying to understand how to reduce or increase pedestrian safety where we do tend to have these accidents. It's a very unique place and perhaps a rich testing ground for this type of work. Now, I also want to be clear that in my mind, this is very much just the beginning, right? So something that we've always had in mind with this work, and we'd love to work on it someday in the future, is this idea that we're currently considering very static variables, right? So we assume we have dry ground, we're on asphalt. But how lighting is going to impact safety is going to change depending on whether it's dry out, wet, snowing. So we'd love to kind of introduce automation and intelligence into this process so that you can imagine these lights would be sort of like self-controlling, right? Depending on what those ambient and environmental conditions are. All right. So to leave you just with a couple closing notes here and sort of some recommendations that came out of our study, I would call these sort of the next steps, is that first, the future tools, like we've been talking about, need to account for this real-world variability in reflectance in environmental features. That's what I'm referring to here. Second, we need to better model how humans are actually perceiving things like glare, accounting for age, which makes a really big difference in your ability to like slow down and stop, adaptation, and also context. Third, light trespass standards should be orientation aware and intersection specific, not just one size fits all, so that when we get to all those weird Pittsburgh intersections, we can actually do something meaningful about it. And fourth, right, standard bodies and manufacturers should start thinking about how to develop intersection-specific luminaire distributions that can start more, I'd say, target pedestrian zones a little bit more efficiently. And using this type of tool could help us get there. But yeah, so we have the tools to support this now. Fingers crossed that we'll be able to continue this in the future. But yeah, with that, I want to thank Korwich, who was the master behind and basically a light savant at this point in terms of how all this physics works. And of course, Steve, for bringing this project to my attention in the first place. It's been really fun collaboration and excited to see where we'll go with it. But thank you so much.
Now we'll open it up to questions. So folks can share their questions with us.
Okay, we already have one in the chat, so I'm going to read this out loud. Katherine, great presentation. 2 questions. How long is the lifespan of this pedestrian lighting features? So that's question 1, and then the second is, how does this design match the requirements for MUTCD?
Lifespan, Korwich?
I'm not sure. So I think with LED, it's probably lasts much longer than the sodium one. Yeah, but in terms of number, I'm not sure. Yeah, but this kind of features you can share with the manufacturing website. Like if you just go to Philips website, they usually have this kind of thing.
Yeah, Steve, I don't know if Steve's online, but this would be something Steve might know too. He's worked with actual different diodes from the manufacturers.
Yes, Katherine.
From above. Yeah.
The life of a typical LED streetlight is averaging around 10 years. So it's about 4 times as long as a typical high-pressure sodium lamp. And that's really the reason why cities are converting from high-pressure sodium to LEDs, is simply because of not only their efficiency in use of energy, but also their less time for maintenance. In other words, changing out the bulbs.
Thank you so much, Steve. We can't see you, but we can hear you it's like very cool.
And then the second question in the chat was, how does this design match the requirements for MUTCD? I don't know what that is. Okay, no problem.
Do you know, Korwich?
What is that?
I don't know either.
Yeah, I'm not sure what that means.
We'll take a look into it.
Great.
And because I'm not familiar with that manual, I'm gonna have to go look at it.
We have a question first.
Yeah, thank you. This is a great tool. My name's Chris. I'm over at Heinz EBN Analytics program. First, I have kind of 2 questions real quick. The first question is, do you think a sort of a cost simulator add-on would be helpful in this software, specifically that as a decision point, the city planner would be interested in the different how the cost differs with the different configurations of the optimized version?
I think that would be amazing. It'd be awesome if we getting in front of the city and talking about this. I think that's going to be something practical that they bring up. They have a budget for how much they can spend on all this, so I think it's a wonderful idea.
Nice. And the second question, as a follow-on, you mentioned that one of the limitations is the trespass policy, that it is standard, more like one size fits all type of limitation. Would you recommend or encourage lobbying or proposing new ways of designing those kind of trespass policies to allow more flexibility in designing different configurations of lighting and interventions?
Yeah, I think it'd be super important, especially if we start seeing, which our results show, that this 45-degree, the policies, right, are very much kind of like based on this 90-degree configuration. When you have the 45-degree configuration, you start getting the lights basically shining directly into the corner, like into where someone's residence would be on that side. And I once again, these are almost more ideas as opposed to questions, and I think they're both very good ideas. Yeah.
Hi, thank you again for a great presentation. Avery Trinidad, actually same cohort as Chris over at Heinz. This is another policy-related question. thank you for producing such a great project. One of the thoughts that immediately came to mind, especially when it came to the city planning angle, was it is an open source project. I assume that it's meant for public use, public implementation. How computationally intensive is it to use?
Yeah.
I am wondering from the standpoint of like data teams in Pittsburgh are robust as they are for the county at large, but I'm thinking of like a smaller, medium-sized city where they're not nearly at the point of maturity, but they are having similar problems with their lighting.
Yeah. Correct me if I'm wrong, Courage, but I mean, quite frankly, the inputs are quite simple, right? So you need to be telling it what the IES file is, and he basically created a way that embeds it. You can basically just say what type you want, right?
Yeah, I think the computation is, well, we say computation, it sounds scary, but it's just something that I can run on my laptop. It's,
It runs on his laptop. It's not something you would change as a user. So you would say what the geometric properties basically are as like an input. You say what the light manufacturer type is. He has like different types you can select from. And then you're not having to do any of the computation. He basically did the pipeline from end to end, right? So you just get the output. And yeah, it runs on his laptop, so super simple. But I mean, riffing off your point, getting a good user interface, I think would be something we'd want to be doing moving forward, right? Not having that reliance on someone having to necessarily open up Python for the first time, which is a barrier for a ton of people, right? So getting a good user interface would be awesome.
Yeah, my question was mostly around like, is this going to burn a hole in someone's GPU?
Oh, no, not at all. Not at all.
That was important as well, thank you.
Yeah, this is fantastic. I'm just wondering if this could be kind of like configured eventually to do non-intersections. So like I'm thinking of just like busy streets, high incidence of pedestrian fatalities.
Yeah, so there's no limitation on the geometric configuration. This could be a street with like a crosswalk. It can be any geometric configuration that you want. Great point. I think areas near like Mellon Park and stuff where they're trying to get people who go between those two parks, it'd be fantastic for something like that.
Any other questions in the room or online?
Next one, I just want to ask if the slides will be shared with us or would it not be?
So this was actually recorded.
Yeah, so this is
Okay.
recorded.
Okay. And I'll post it on the Safety 21 website after this. Thank you.
Yes.
This is just sort of a final thought, and I guess it's closer to Chris's questions where I guess it's more of a comment and suggestion.
I'd love to hear the.
Maybe even just like a basic starter guide for future users. I assume being an open source product, there probably is something to that effect. But honestly, even just like a starter kit for those teams within, again, those less resource cities.
Yeah.
Because again, this is it seems like something a lot of city planners can get a lot of use out of.
Sure.
Yeah.
No, it's a great idea, and even, I mean, you guys coming from Heinz, like doing capstone project related to this or something moving forward, I think would be a ton of fun, and we could really kind of move this towards that.
yeah, and on that point, we have recently published a new tutorial. It's a Medium article, just like go through like basics of like from getting the IES file, how to like just like a simple line, things like that. So we have it on GitHub. So it's good.
Thank you.
Thank you, Katherine. And to all of today's attendees, thank you for joining us. And like Selena mentioned, today's presentation will be posted on the Safety 21 website's What's Happening page, along with a link to the video presentation. And for students who are interested in engaging in transportation topics, the Transportation Club on campus is like a great way to plug into your transportation topics with fellow transportation enthusiasts. And again, thank you for attending the Safety 21 Connection Seminar, and we hope you'll be able to join us again in the future. So in the meantime, feel free to contact us with any questions. Thank you.